Time appropriate greetings everyone and welcome back. In this video we're going to quickly solve a linear program involving 4 variables, and then we're going to analyze it using a sensitivity analysis. We're going to see how far this linear program can bend before the solution breaks. We have 5 food items, items A, B, C, and D. They're on a menu. Each item has calories, protein, carbs, fat content, and each product has a cost. We got Arnold here who wants a diet with a minimum cost. He wants to spend as little money as possible, but he still needs his dietary requirements met. He needs at least 500 calories, 6 grams of protein, 10 grams of carbs, and 8 grams of fat. I suppose this is a diet just for one meal. As before, we're going to solve this linear program by first putting in some dummy variable values. These will change when solver takes care of the solution. I'm going to copy the coefficients of the objective function in. These are the costs for each item. And I'm going to copy the coefficients for the constraints. These are the dietary values for each item. I'm then going to compute the totals here. Now, as before, I'm going to take the value for item A times the cost for item A. I'm going to take the value for item B times the cost for item B. I could do this like I did before and just take the value times the coefficient plus value times the coefficient, etc. This becomes time consuming, especially if you have 10 variables here. I'm going to show you that there's actually a better function in Excel for this. Excel has a function called SUMPRODUCT. And SUMPRODUCT takes 1, 2, 3, 4, however many arrays you want, and multiplies them, product, and then adds up the answers. So if I take SUMPRODUCT this array, comma, this array, it's going to take each pairwise comparison and take their product and add them up. That's exactly what we want, $1.80. Now I want to autofill this total down, so I'm going to add absolute references to the rows of the variable cells. Autofill this down, and I get the total calories, protein, carbs, and fat. I'm going to delete these in the middle here. I'm going to change the decimals so that they're whole numbers. So what we have so far is that if we have one of each item, it'll cost $1.80, and I'll get 1250 calories, 5 grams of protein, 12 grams of carbs, and 12 grams of fat. Now I want to put my limits in. 1250 is the value of the calories constraint right now. I want this to be greater than or equal to 500. Arnold wants at least 500 calories. This needs to be greater than or equal to 6, at least 6 grams of protein. Right now, one of each isn't meeting that constraint. Carbs needs to be at least greater than or equal to 10, and fat needs to be greater than or equal to 8. Notice again that one of everything is not a feasible solution because it doesn't meet the protein constraint. It meets all the other ones, but it doesn't meet the protein constraint. Let's now quickly solve this linear program. Head up to the ribbon, Data tab, open up the solver dialog. We'll set the value of the objective function, total cost, to a minimum. We'll change the variable cells here. These are the values that are just playing placeholder. We'll have solver manipulate those to get a minimum cost. And we'll add our 4 constraints. So we'll add a constraint. Total calories needs to be greater than or equal to 500. Add our second constraint. Total protein needs to be greater than or equal to 6. Total carbs needs to be greater than or equal to 10. And fat needs to be greater than or equal to 8. Hit OK, and we have our 4 constraints listed in the constraints box. Ensure that onConstrained variables non-negative is checked so that we don't have negative values of the number of items consumed. Choose Simplex Linear Program as your solution method, and click Solve. Solver informs us that we have found a solution. None of item A, 3 item Bs, 1 item C, and no item Ds. In the Reports box, check Sensitivity, and click OK. So as of right now, we're where we were in the last video. Solver has found a solution. If we buy 3 item Bs and 1 item C, we meet our dietary requirements at the minimum cost of 90 cents. This time though, we also have a sensitivity report tab created. I'm going to copy and paste the sensitivity report and paste it into the main sheet. What is a sensitivity report and what is it going to tell us? Well, there are 2 ways that a linear program can change. First of all, the coefficients of the objective function might change. For example, right now it costs 50 cents for item A, 20 cents for B, 30 cents for C, 80 cents for D. It's possible that maybe the price for item C goes up to 40 cents. So that would be a change to the linear program. It's also possible that the constraints could change. What if all of a sudden Arnold needs 600 calories or needs 10 grams of protein? It's possible that the limits on the constraints of a linear program could change, and that would result in a different linear program. Now, there are two possibilities. If I change a constraint, or if I change a cost, aka a coefficient of the objective function, it could change the solution, or it could not. For example, if item B costs 30 cents instead of 20 cents, would we still want to eat 3 of them? Or maybe because this is more expensive, we'd go to another food item. In short, how much can we change the coefficients of the objective function and the limits of the constraints before the solution of the linear program changes? Before it is no longer desirable to have 0, 3, 1, 0 as your number of items to reach the minimum cost. Answering this question is done by this sensitivity report. The variable cells section tells you everything you need to know about the coefficients of the objective function, whereas the constraints section tells us everything we need to know about the limits on the constraints. Let's look at the variable cells section first. Notice that we have the objective coefficients here. These are the costs that we used in the original linear program. I'll make this column a little larger so we can see the item names. So item A originally cost 50 cents, B 20, C 30, D 80. For each of the items, we have their coefficient and allowable increases and decreases. If I look at item B, I see the allowable increase and decrease of 18 cents and 5 cents. The allowable increase and decrease tells you how much the coefficient can move up or down, so in this case, how much the cost can increase or decrease before the solution for the linear program will change. So if I change the price of item B from 20 cents and I increase it by less than 18.3 cents, I'm still going to buy 3 item Bs. The solution will not change. If I increase the cost of item B by 20 cents, so from 20 cents to 40 cents, a 20 cent increase, that's more than 18 cents, and that's more than I'm allowed, I need to resolve the linear program. The solution will change. If the price of item B goes down by more than 5 cents, so maybe I take it from 20 cents and I lower the price down to 12 cents, that's an 8-cent decrease. That will require resolving the linear program. But if I change the price to 30 cents, 20 cents bumped up to 30 cents, that's only a 10-cent increase. 10 cents is less than the allowable increase, which means I'm still going to buy 3 item Bs. The solution will not change. On top of giving the cushions on each coefficient before needing to resolve the linear program, the sensitivity report will also give what are called reduced costs. Notice that it is too expensive to consume any of item A or any of item D. Their cost is too high compared to the nutrition that they provide. So to minimize costs, you just don't buy any. You only eat item B and C. The reduced cost says how much do I need to decrease the cost, decrease the objective coefficient before it becomes viable to buy one of these items. How low does the price of item D have to go before buying item D becomes worth it? 50 cents. Right now, item D costs 80 cents, so it would have to go down to 30 cents. It would have to be dropped by 50 cents in order for this to become a non-zero solution. Notice that the allowable decrease is also 50 cents, because clearly, if you start making item D worth it, it's going to be a new solution and you need to resolve the linear program. So the reduced cost tells you how much does the objective coefficient have to change so that the final value is non-zero, so that you actually want some of item D or item A. In the constraints table, we have the final values, which are the values that we got from the solution. So when we have 0, 3, 1, 0, we have 750 calories, 6 grams of protein, 10 grams of carbs, and 13 grams of fat. That's reflected in the table here. And then we have the original constraints, right-hand side over here, 500, 6, 10, 8, 500, 6, 10, 8. These allowable increases and decreases are for the limits on the constraints. So if I change the calories required to 600, the solution will not change because 600 is only an increase of 100. It's 100 more than 500, which is less than 250. If I change the required protein to 8 instead of 6, that's a change of 2, which is less than the allowable increase. So the solution will be the same. If I require 12 grams of protein, 6 to 12 is a change of 6, that's more than the allowable increase, I'd have to resolve the linear program. So the allowable increase and decrease mean the exact same thing. How far can I push this program before having to resolve it? Except the allowable increase and decrease apply to the limits on the constraints rather than the coefficients of the constraints. I'd like to make a note now that this 1e plus 30, you can read that as infinite, no limit. It's 1 with 30 zeros after it. So if I were to change the calories required from 500 to 0, that'd be allowable. This basically means you can decrease it as much as you want, or up here, you can increase the coefficients as much as you want. The constraints table also includes this column called shadow price. The shadow price says how much does the value of the objective function change. In this case, that's the total cost. How much does the total cost change when you increase the limit on a constraint? For example, this shadow price is 0. So if I were to increase the number of calories from 500 to 600, again, that's within the allowable increase, it would cost nothing extra. This makes sense, of course, since I'm already getting 750 with the solution I have. So if I needed 600, this solution, which is the same, would still meet that requirement. Note that the shadow prices are valid only within the allowable increase and decrease. The shadow price for protein is 0.025. That means if I were to increase the protein requirement from 6 to 7, which is allowed because the allowable increase is 4 and 6 to 7 is only 1, that would increase the price by 2.5 cents. If I were to increase the protein requirement from 6 to 8, an increase of 2, which is also allowed because it's less than 4, it would increase the cost by 5 cents. 2 times 2.5 cents. If I were to increase it by 3, it would go up by 7.5 cents. The shadow price says that for each unit that you increase the right-hand constraint by, that's how much you'll change the value of the objective function. If I were to increase the carbs from 10 to 20, which is allowed because the allowable increase is infinite, I'm allowed to increase the amount of carbs as much as I want. So if I were to require 20 instead of 10, the price would go up by 10 times 0.075, 75 cents. So this solution tells us how much we need to buy in order to meet our dietary requirements, and the sensitivity report produced by Solver tells us how we can change both the cost of the items, the objective coefficients, and the dietary requirements, the constraint limits, how far we can change them without breaking the program and requiring resolution. It also tells us how much our cost will go up when we increase our dietary requirements, and how much things need to cost before they become worth buying.